Alright, so in this video we are picking up from the naming of benzene compounds. So welcome back. Alright, remember to subscribe. Alright, so we are looking at now the reactions of benzene. Two of them you will have to know the mechanism for. Alright, the others are just equations. So the first one we are going to look at is the nitration of benzene. Now the mechanism for which benzene reacts is called electrophilic aromatic substitution. It's the aromatic benzene, it's the ring, or it's an aromatic compound, and it's electrophilic substitution. So there's the electrophilic aromatic substitution. Alright, so the nitration of benzene is a pretty simple mechanism. So the first thing that we will need to do, alright, so let's represent it with an equation first. Alright, so benzene, we will have benzene, we will generate our nucleophile. In this case, it's the nitronium ion, alright, and you will get nitrobenzene. Alright. Now this reaction, it uses sulfuric acid, concentrated sulfuric acid, and concentrated nitric acid. That is how we are going to generate our electrophile, which is the nitronium ion. Right? So it's basically benzene the presence of sulfuric acid and nitric acid, temperature of about 50 degrees Celsius, you will get nitrobenzene. So if you want to convert benzene to nitrobenzene, concentrated sulfuric acid, that's the catalyst. You use the nitric acid to generate the electrophile, which is the nitronium ion, and the temperature of about 50 degrees Celsius. Alright? So let's do the mechanism now. So the first thing that we need to do is to generate our electrophile. So for that, we react nitric acid with sulfuric acid. And we get our electrophile, which is the nitronium ion. Alright, so when we react nitric acid with sulfuric acid to get our electrophile, the nitronium ion. Alright, so that's what we will do first, generate our electrophile. So now it's time for the mechanism. Alright. So step one. So when the electrophile approaches the benzene ring, we know that the pi electrons can attack any nucleophile, any electrophile, right? Because we know that pi bonds, they have the p orbitals with the lone pair of electrons, and once you have a lone pair of electrons, you can form a dative covalent bond. So two electrons are going to be donated to the nitronium ion. So we need to draw a curved arrow. So remember, we use a curved arrow to show the movement of two electrons. So we are moving the two pi electrons to form a bond with the nitronium ion. That is where the double bond is going to be broken, because double bond consists of sigma bonds and pi bonds. The electrons in the pi bond, that is what is going to be used to form the bond with the nitronium ion. So we will no longer have a double bond at this one. So remember, as I was showing you in part 1 of this series, right? Once this bond is broken, this carbon only has 3 bonds, so it will get the positive charge. So in step 1, the pi electrons attack the nitronium ion. Alright, so the movement of electrons from the pi bond to the nitronium ion, right? And then we get the benzene ring or the uranium ion because it has a positive charge, alright? So you can put to form the uranium ion, alright? So that's what happens first. Now, you could show the resonance structure, but you don't have to do that for keep, alright? If you pursue it further on, then you show it, alright? So, the pi bonds, one of the pi bonds, you can use any one, by the way, this or this, it doesn't matter. One of them attacks the electrophile, and they show it here. The bond is broken. This carbon, it only has 3 bonds, remember, 1 bond from the hydrogen, right? So that is why it is positive. And then in step 2, let's draw back this, right? So sulfuric acid is a catalyst, right, in this reaction. And the catalyst, when you use it, one of the features of a catalyst is that you must generate it at the end of the reaction. So HSO4, right? Then one of the lone pairs on the oxygen atom is going to remove the hydrogen from this carbon. So the hydrogen that is attached to the carbon with the NO2 group, it is going to be removed. And so the 2 electrons, remember every bond has 2 electrons. This bond is not being broken homolytically because 2 electrons were donated to this hydrogen atom. So it means that hydrogen is not taking any of the electrons. So the 2 electrons in this bond are used to restore the double bond in the benzene ring. of course we get back sulfuric acid. So a hydrogen ion is removed, right? And the double bonds are placed back into the ring. Well, the electrons return to the ring to form the double bond here. So that is how benzene regains its stability. So remember, the reason why benzene is doing substitution is because it wants to maintain its stability, and it is stable when it has its pi system, which is the 3 pi bonds present. Alright, so nitration is pretty simple. You just write the equation to generate the nitronium ion. And again, for K, you don't need to draw the structure of the nitric acid and the sulfuric acid and show all of that. When you go to university, then that will come into play. Alright? So that's the equation. You generate your electrophile. You know that one of the pi bonds will attack the electrophile, and so now the electrophile is attached to the ring. One of the carbon is positive. In the second step, the hydrogen is removed and the electrons are returned to the ring. So we get back the double bond, and that is electrophilic aromatic substitution, specifically nitration of benzene. Alright, so that's the mechanism. We are going to do the next one now, which is the halogenation of benzene. Alright, so this one is the halogenation of benzene. And the catalyst, so for the benzene reactions, they need a catalyst, or else the reaction will occur slowly. Alright, so for if you want to add a halogen to the ring, for bromine, use FeBr3. Alright, so again, just like with the nitration of benzene, the catalyst makes the bromine more electrophilic. Alright, so in terms of the mechanism, alright, when this complex approaches the benzene ring, same thing again will happen. We have the nucleophile donating a pair of electrons, so it is going to remove this bromine atom. So this bond breaks heterolytically, and we get bromine being attached to the benzene ring. Alright, so you have the complex, so you just write the equation, right? And then now, in terms of the mechanism, we know we should have the nucleophilic attack, right? So we remove a bromine atom from the complex, alright? This bond breaks heterolytically, so this bromine atom gets both electrons. So we end up with FeBr4 along with the bromine attached to the benzene ring. And then in the second step, you draw back this. So remember, benzene needs to go back to being benzene with the 3 pi electrons. So again, this hydrogen needs to be removed. So now the electrons from this bond are going to be used to remove a hydrogen and the two electrons between the bond with the carbon and the hydrogen will return to the ring, right? And so, with that said, or that done, we get bromo, benzene, bromobenzene, HBr, and FeBr3. Alright? So all you need to do is just practice the mechanism. Alright? So that's it for the halogenation of benzene. So these are the two mechanisms you must know: halogenation and nitration. Alright, so after those two mechanisms, the next reaction that you must know is one involved in phenylamine or aniline, and that is a diazotization reaction. So whenever you react an amine, right, with hydrochloric acid and nitrous acid, so it's not nitric acid, it's nitrous acid, HNO2. So any amine with nitrous acid and hydrochloric acid, you are going to get a diazonium salt. So the reaction is not with the benzene ring, but with the amine group. So it is diazotization is a reaction of amine, right? So it has nothing to do with the ring. So the amine with nitric acid and HCl, you get not nitric acid, nitrous acid and HCl, you get a diazonium salt. So you just pay attention right here. So this salt, it should be a nitrogen to nitrogen triple bond with the chloride ion. So for this, you just need to know the products. So when I react amine, phenylamine with nitrous acid and HCl, this is the product you must get. Alright? That's the diazonium salt. Good? Now this is unstable, so you need to keep it cool. So the reaction condition, keep it to 5 degrees Celsius or less. Alright? Now a second part to this reaction now, when you have the diazonium salt, right? If you react it with phenol, right? So this is the benzene, the diazonium chloride. You react it with phenol, you will get a compound. We call them azodides. So the class of compound, when you react phenols with benzene, with a diazonium salt, you will get an azodide, alright? And they are brightly colored, right? So they are using the clothing industry, alright? So this particular reaction, where you react phenol with a diazonium salt, is called coupling. So up here, this reaction up here, that's diazotization, in which you get a diazonium salt by reacting an amine with nitric acid and hydrochloric acid. If you should react the salt with phenol, you will get a dye. That reaction is called coupling. Alright? So diazonium salt with phenol, you get your azodide. Alright? That's it. So you just need to know the reactants, products, and the reagents used. So the phenylamine, these reactants, remember the condition as well. Remember how much bonds you have here? 3 bonds. But when you have the dye, it's 2 bonds. Alright? So these are 2 more reactions that you must remember. And these tend to come in a reaction scheme. So you could get this and ask for the reagent, and then go from here to the dye, and you're asked to fill in the blank. Alright? So just study the structures and the reagents. there's no mechanism or that sort of thing. Just nitration and halogenation, that's the mechanism. For these, just know to draw the structure of the reactants and the products and know the reagents. Alright? So that's diazotization, this is coupling. Alright, so we're looking at some reactions of phenol. So the first one is phenol with bromine, and you will get 2,4,6 tribromophenol. In terms of observation, you will get a white precipitate, and in terms of scent, it is an antiseptic one. You should also know the reaction of phenol with the acyl chloride. When you react alcohol with acyl chloride, you get an ester. Right? In this case, it's phenyl ethanoate. So these are two reactions of phenol that you must know. Alright, so again, all you need to know is the reagent and the product. Phenol with bromine, 2,4,6 tribromophenol, white precipitate. Phenol with an acyl chloride, you get an ester. Alright, and you would also get HCl, the chlorine and the hydrogen. Alright, so the last reaction of phenol that you need to know is the reaction of phenol with sodium hydroxide. The sodium metal will replace the H, will replace the hydrogen, so you will get sodium phenoxide. Alright, and moving on from phenols, if you reduce, you can get phenylamine from nitrobenzene by reduction. So nitrobenzene can be converted to phenylamine. If you use tin and concentrated hydrochloric acid. So again, know the reactants, know the products, and the reagent. You can convert nitrobenzene to phenylamine using tin and hydrochloric acid. Alright, so the last reaction is still nitration of benzene, but we are comparing methyl benzene with nitrobenzene. Now if you remember, I said alkyl groups in the previous video. Any alkyl group that's an activating group, it makes the ring more reactive. So any group you're adding will go to the ortho and para positions. So you will predominantly get a mixture of ortho nitrobenzene and para nitrobenzene. Remember, ortho position 2, para is position number 4. And we know that the nitro group is a deactivating group. So if you're adding an next nitronium ion to the ring, it will go to the metal position, because we know that the deactivating group are metal directors. So if you are nitrating methylbenzene and nitrobenzene, you have to know where to put it. Or anything you're adding to the methylbenzene, you have to know it goes to ortho and para. If it's phenylamine, it's the same thing. Know the group. If it's meta or ortho-para director. So, the next question they ask, you compare the reactivity of methylbenzene, nitrobenzene, and benzene. So if you are given 3 compounds, like benzene and 2 others, you need to know if the group attached is activating or deactivating. So we know that benzene will be in the middle in terms of reactivity, because the nitrobenzene, the nitro group, is a deactivating group. So it makes the ring less reactive. So nitrobenzene is less reactive than benzene, because it pulls electrons from the ring, making it less reactive. Methylbenzene, on the other hand, now is more reactive than benzene, because the methyl group releases electrons to the ring. So the electron density around the ring is higher. So methyl benzene is more reactive than benzene, which is more reactive than nitrobenzene. Alright? So in terms of comparing these three, methyl benzene would be the most reactive, and the nitrobenzene would be the least reactive. And of course, benzene would be in the middle. Alright, so that's it for the benzene, reactions of benzene, naming and all of that. Alright, so just practice the mechanism, study the reagents and what you get when you react certain things. Alright, remember the auto-para positions, all of that, meta, auto-para directors. Alright, so in other videos we will work some questions, but if you don't know your reagents, then you're already in trouble. Alright, so that's it. Alright, so remember to give the video a like and share. If you have any question, you can ask in the comment section.